Hi, I'm Vinyashri. I'm from AID's department. I'm going to present Cuda matrix addition, kernel execution, and grid indexing analysis. Understanding unified memory performance patterns and kernel launch configurations in Cuda matrix operations. Execution context, the code overview. This code implementation performs matrix addition using unified memory, measuring performance with NV-proof profiling. The kernel leverages 2D thread blocks mapped to a 2D matrix structure. Key optimization, warm-up kernel execution migrates unified memory pages from host to device before timed runs. We can see that in the images right there. Okay, kernel function sum matrix GPU. This is the code for global void sum matrix GPU. This qualifier designates this function as a kernel callable from host code and executable on GPU device. Thread index calculation. One, global X coordinate. It combines thread's local X position within its block with the block's position in the grid scaled by block width. Second, global Y coordinate combines the thread with Y position within its block with the block's position in the grid scaled by block height. 3. Linear array index converts 2D coordinates 1D array index using row major order, row offset plus column position. Thread to matrix mapping. Each thread processes exactly one matrix element. The 2D grid block thread hierarchy maps naturally to the 2D matrix structure with representing the element's row column position. So kernel launch configurations, warm-up launch, sum matrix GPU, processes only one by one submatrix triggers unified memory migration from host to device, establishing optimal page placement for subsequent operations. Full computation processes thus complete an X and Y matrix with pages already resident on device from warm-up. This launch measures true computational performance without migration overhead. Grid and block dimension configuration. Grid calculate as ceiling division to cover entire matrix. Total threads launched typically exceeds matrix size. Boundary checks handle edges. So grid.x is nothing but that is equal to nx plus 31 by 32 as well as for y also. And then unified memory performance impact. Initial state, matrix data allocated on host. No GPU slide pages established it. 2. Warm-up phase. First kernel access triggers page migrates the device. Significant overhead observed. Timed execution. Data resident on GPU. No migration. Pure compute performance measured by NVPro. This two-stage approach isolates memory transfer cost from computational throughput in profiling results. Key performance consideration, memory coil scheme, occupancy synchronization. So memory coil scheme, row major indexing enables co-scale memory access, threads in a wrap access, consecutive addresses, maximizing memory bandwidth utilization. Occupancy, 32 by 32 thread blocks achieve high SM occupancy on most NVIDIA architectures, hiding memory latency with computation. Synchronization, CUDA device synchronize. It ensures kernel completion before timing measurement, critical for accurate performance profiling. Summary, thread launchers, index computations, boundary validations, memory operations. Thank you.